writing our code all in a single file. But as our programs get longer, our main logic tends to get buried underneath all of our function definitions, which can make the program hard to read. So, easy solution, what if we just took all those function definitions and moved them somewhere else? That means organizing our code into modules. To create a module, we just make a new file with a .py file extension. File extensions tell the computer how to interpret the file's contents, like MP4 is a video, and .py is Python code. We'll name this file arcade.py, because it's meant to contain functionality for an arcade game. And then we'll just move all those function definitions in here. If I run the program now, I get a name error, because the computer doesn't know where to find those functions anymore. It may seem obvious to us that there's another file over here, but the computer doesn't put 2 and 2 together. It only does exactly what we tell it to do. So, if we want the computer to be aware of the arcade module when it runs the program, we need to import it. Anytime we call one of its functions here then, we need to prefix it with the module name. Alright, that concept is pretty straightforward. We just have our code in multiple files now. But let's unpack how exactly this all works. Even though our program logic may be spread across multiple files, when we run a program, we can only ever specify a single file to execute. We call this the entry point, or main logic. By convention, in Python, we name this file main.py. You may have noticed that in the Khan Academy IDE, the default file is always named main.py. When we press the run button, this is the file that executes. We can build up a program by having a function in one module call a function in another module, which imports another module, and so on and so on. But for any code to be executed, it needs to be triggered somewhere along the chain from that entry point file. Okay, what about this import statement? How exactly does that work? When the computer executes an import statement, it jumps execution to the specified module. When it's done there, it'll jump execution back to the importing module and pick up from where it left off. From the computer's perspective, importing a module is effectively the same as copying and pasting all of the contents of that file where the import statement appears. But there's one key difference: the scope. Function and variable names are scoped to the module that they're defined in. This just basically adds another layer, so in the computer's memory, all those function names are filed under the module name. That's why if we call getScore in main.py without the arcade in front of it, we get a name error, because the computer can't find that name in main's global scope. By putting the arcade in front of it, we make it a two-step lookup. First, the computer looks in its memory for the arcade namespace, and then in that scope, it looks up getScore. Module scope means that as a programmer, I don't have to worry about what other programmers or myself yesterday are naming their functions in other files. We can both name our functions getScore because they'll exist in different scopes. Note that we typically only put function definitions inside a module, because the net effect of executing that is just that the computer has learned some new tasks. If I add a print statement indented at the top level of this file, it executes anytime I import this module. If that module imports another module, and all of them have these top-level print statements, it becomes very difficult to trace where that output is coming from. So why use modules? Well, they're really just a convenience for the programmer. We break down our tasks into functions, and then we group those functions into modules. Well-written modules make programs easy to navigate, because if I want a piece of functionality related to inventory management, I would know to look in the inventory module. They also make code more reusable, because I can package a bunch of related functionality into a module and then import it in multiple places. And they let us focus on one thing at a time as we're building. When I'm working in main.py, I can think about my program at a high level and just work on how all the pieces fit together. And when I'm working in inventory.py, I can forget about all that and just focus on the details of how inventory management works. Let's design a program with multiple files. We want to build a basic version of the strategy game Nim. In Nim, players take turns removing either 1 or 2 stones from a pile. Whoever removes the last stone loses. In the version we're building, we want the user to play against a computer player. That means we'll probably want a function that decides how many stones the user picks up, and a function that decides how many stones the computer picks up. Let's start by creating a new module for our game components to live in. I think I'm going to name this stones.py because at the very least I know I'm going to have some functions for picking stones. I'll name one pick for user and the other pick for computer. I don't want to get too stuck on this detail right now, so I'm going to have the computer always pick one stone, and I'll figure out a better algorithm later. The user, on the other hand, needs to pick their number of stones via input prompt. So in pick for user, I'll call the input function, and then I'll return out the number of stones that the user entered. However, we want to make sure that this function can only ever return 1 or 2. So we can use a loop to validate the user's input. If they don't enter 1 or 2, we repeat the prompt. Now that we have a couple functions sketched out, let's switch over to thinking about the main game logic. So I'll jump to the main.py file. The game continues with players picking stones until the pile runs out, which kind of sounds like a while loop. While there are still stones, play a turn. So, like with all while loops, we'll initialize our pile before the loop. In the loop condition, we'll check if the pile is greater than 0. And then inside the loop body, we need to update pile. So we'll call pick for user and subtract that number of stones. We defined pick for user in the stones module. So in order to call the function, we'll need to import stones and then prefix the function name. Okay, let's pause and test that our loop works. Because there are 10 stones, if I pick up 2 every time, the loop should terminate after 5 iterations. Now let's add in the computer player's turn. Just like the user, the computer will pick a number of stones and remove those from the pile. But we can't just put this in the loop body after the user's turn, because what if the user has already picked the last stone? The computer shouldn't get another turn, because the game's already over. Instead, we want to alternate players on each iteration of the loop. So we'll add a new variable to keep track of whose turn it is. Since there are only 2 possible states, we can make this a Boolean. If it's true, we play the user's turn, and if it's false, we play the computer's turn. Then at the bottom of the loop, we just swap it to the other player. If it's true, we change it to false, and if it's false, we change it to true. Okay, let's try this out. It seems like we have a pretty good working prototype here. So now it's time to jazz up the user interface. First, I think it would be nice if the program told us who won. We know the game is over after the loop has terminated, so we'll print out the result here. Whoever went last must have picked the last stone, but we already swapped over the turn at the bottom of the loop. So if it says it's the user's turn, then the computer picked the last stone. And to make it clear that you don't want to pick the last stone, I'll print out the rules at the top of the program. It might also be nice to draw the pile of stones. I'll define a new function for that, so I can change up how the pile looks without having to touch my main logic. The function will take in a number of stones as a parameter and return out a picture. Let's maybe draw a little circle for every stone. Then back in main.py, I can just call show and print out its result. These circles look cool, but they're a little annoying to count, so I'll go back to the show function and include a number in the picture. Now let's playtest. We'll run through the program a few times and see if anything feels off. The strategy isn't really all that interesting. If the game always starts with the same number of stones, I would just do the same thing every time. So let's randomize that pile size with a new function. That's much better, but it's still not that interesting because it's pretty obvious that the computer is always picking 1 stone. At the very least, it can randomly return 1 or 2. But we want to make it a bit smarter than that, so it should take the number of remaining stones into account. If there's 1 stone remaining, then the computer has no choice but to pick 1. If there are 2 stones remaining, its best option is to pick 1 stone, so it leaves the opponent with the last stone. Similarly, if there are 3 stones, it should pick 2. But what if there are 4 stones? It seems like no matter what you pick, you're kind of in a bad position. Because if you pick 2, then your opponent can pick 1 and leave you with the last stone. But if you pick 1, your opponent can pick 2 and still leave you with the last stone. This gives us an interesting insight. If the computer can leave its opponent with 4 stones, then it's won the game. So if the computer has 5 stones remaining, it should pick 1 to leave the opponent with 4 stones. And if it has 6 stones remaining, it should pick 2 to also leave the opponent with 4 stones. Okay, let's implement the algorithm that we have so far. If we have 1, 2, or 5 stones, we want to pick 1. And if we have 3 or 6 stones, we want to pick 2. Otherwise, by default, the computer will just pick randomly. Let's test real quick that all those cases work. Back in main.py, I'll call pick for computer with a few different arguments, just to make sure I get back the return values I expect. The computer seems to be a worthy opponent now, but there's still room to optimize the computer's algorithm. What's its best move if the pile has 8 stones, or 9? I'll leave that as an exercise for the viewer. Hint, there's a pattern if you map out more numbers. You've broken your program down into functions, but now maybe you have hundreds of functions, and a team of programmers is in there every day making changes to the code. With all of these moving pieces, how is it possible that this program isn't constantly broken? The secret? Testing. Tests can come in many forms, like performance tests or end-to-end tests, but the most common is unit testing. Unit tests test a single unit of functionality at a time. In most cases, that unit is a function. With unit tests, we can define the requirements for our function in code. For example, my unit test might validate that when I call my function with the arguments 5 wheat and 1 ore, that I get the return value false. If that assertion is correct and I do get back false, then the test passes. But if we get a different return value from the one the test expects, then the test fails. Teams can automate their unit test to run anytime someone makes a change to the function, and they can block that change from being submitted until all the related unit tests pass. This effectively enforces the requirements, so programmers don't accidentally break things when they make a change. Either we fix the function to make the unit test pass, or if we thought twice about it and we're confident that it's safe to change the requirements, then we can update the unit test to reflect that new expected behavior and submit that along with our code change. That way the unit tests stay a living contract of the function's requirements. But how do I know which tests to write? Writing just one test case doesn't really do a whole lot, because my unit test would still pass even if my function just always returned 4. So I haven't really proven anything about my function logic. I could write a test for every possible input value, but that's probably not the most efficient use of my time. Instead, programmers try and work for a goal of code coverage. As a whole, we want our test cases to execute every possible path of execution through the function. So we try and identify different classes of inputs and write a test case for each of those. For example, with our getRouteScore function, we would at least want a test case for each of these conditional branches. So our classes of inputs would be less than or equal to 2 trains, 3 trains, 4 trains, and greater than or equal to 5 trains. With those representative inputs, we've anticipated and proven out all the reasonable ways that someone might call our function. Of course, the testing process isn't always perfect. We may miss a test case, or we might make compromises on code coverage in the interest of time. If we do find a bug later, we just want to make sure we learn from that mistake. So most programming teams will go back in and add a test for that exact failure case, to enforce that the same bug never happens twice. Okay, great, but how do I actually write unit tests? The principles stay the same, but the exact syntax varies depending on which unit testing framework you use. In Python, many programmers use the unit test module or the PyTest module. Here's an example test suite, written with the unit test framework. I have 7 test cases, and you can see that they're basically all the same. I only change the name, the argument I pass to the getRouteScore function, and the expected result I compare to. When I run it, I can see that one of my test cases is failing. It tells me the name of the failing test case and the assertion that failed. Here, I got the result -2 instead of the expected 0. So I know my function must have a bug somewhere, because it doesn't work when I call it with a negative argument. As you can see, a lot of unit testing code is just boilerplate. That is, the same repeated required syntax. So a lot of programmers will just copy and paste the boilerplate. That means the secret to unit testing isn't so much memorizing the syntax as it is learning how to identify interesting test cases. If you're a beginner programmer working independently just to learn, then I'll be honest, it may not be worth it to write unit tests for all your code at this point, because writing test code can often take just as long as it takes to write the program code. However, it is worth your time to think about test cases. When you write or change a function, it's a good habit to call it with a few different arguments to verify that it works as expected, even if you're not automating that process with unit tests. That way, as we build out the rest of our program, we can have confidence that the individual functions work correctly. And when we inevitably encounter an error later, we can rule out those functions as the cause of the bug. Let's apply test cases to debug a racing game. Our game prototype has 2 cars that race on a straight track. Each round, the cars move forward a random number of spaces, and whichever car passes the end of the track first wins. Let's take a look at the code we have so far. We use a while loop to repeat rounds until the race is over. On each iteration, we move the cars, we print the status of the race, and we display the track state. When I run it, it kind of seems like this game works. But there does seem to maybe be a little bug here. On the last round, it seems like cars are sometimes disappearing from the track. So maybe I'm missing something in my display function. I'm going to open up the track module to see how this display function works. It takes in the positions of the 2 cars and the length of the track, and it returns out a string drawing of the track state. Seems reasonable, but what's going wrong then? To narrow this down, I'm going to test the display function in isolation. So I'll pop back over to main.py and run through a few test cases. There's the case where the first car is ahead. There's the case where the second car is ahead. There's a case where both cars, I guess, are on the same position of the track. And then there's the end case, where a car is beyond the end of the track. Okay, let's see what values we get back. I'm going to comment out this game loop for now, because its output is a little distracting. It looks like a car is disappearing in 2 test cases. So, lucky us, maybe we have 2 bugs to fix. Let's start with the last case, where a car's position is greater than the track length. What do we want to happen in this case? Well, I'd like to still see where the car is. So maybe we just keep drawing until we reach the furthest position. Right now, our draw loop only goes up to the length of the track, but +1 since range is exclusive. So if the track length is 5 and car 1 is at position 7, then we want to keep drawing segments until we pass position 7. So really, the end of the range should be whichever is greater, the position of car 1 or the end of the track. But car 2 might also be the furthest, so we should really take the maximum of all 3 positions. Let's see if that fixed the problem. And let's double check the case where car 2 is the furthest. That's 3 test cases passing now. So let's wrap this up by fixing the case where the cars are at the same position on the track. Right now, it looks like display is only showing the symbol for car 1. What do we expect? Well, it's not all that obvious. One solution might be to just draw a different symbol that indicates both cars are on that space. I can change the symbol later, but for now, let's just say I draw an X. So let's go back to our display function and see what we need to modify. It looks like this nested function call controls which symbol we draw for each segment. So we need to update the get symbol for space function to handle that X case. If car 1 and car 2's position are the same, then we return an X. Everything is an X now. What did we do? It seems like for every segment, get symbol for space is returning X. We do need to check that car 1 and car 2 are at the same position, but we also need to check that that's the position we're currently trying to get the symbol for. It doesn't matter if car 1 and car 2 are both at position 5, if right now we're trying to get the symbol for position 1. So to draw an X, all 3 of these values should be the same, which we can verify by checking that position equals car 1. Alright, all 4 test cases are passing. I'm fairly confident that the display function works now. So let's put the game back together. I'll clean up those test cases and uncomment out the game loop. The next time you encounter a bug in your program, try narrowing it down to the individual function level. And hopefully you'll have an easier time debugging just that one unit of code.